Greetings to all. So in this video we are going to discuss about some problematic questions related to basic system design. As we discussed in our last video, so this is about the syllabus of unit 5. So we have problems on basic system design. So already we discussed in our last video that the basic system design verifications that can be done through two factors or two methodology. One is power budget, second one is rise time budget. So power budget is nothing but it is a ratio of PT by PR expressed in decibels. That is total power loss by receiver power loss expressed in decibel, and it is the amount of acceptable loss that can be incurred. Next one is rise time budget. So it's an analysis. It's a convenient method to determine dispersion limitation of an optical link. So only based upon this power budget and rise time budget we can able to come to the conclusion that whether the system design is adequate or not. So power budget involves the power level calculations from the transmitter to the receiver. So what are the factors that has to be considered for both the calculations? One is attenuation, coupled power, other losses, equalization penalty, SNR requirements, minimum power at detector, bit error rate, safety margin, and so on. Consider an example. So this is the actual formula. The optical power budget is then assembled taking into account all these parameters together. So we can write it as Pi, which is equal to P naught plus CL plus MA plus DL in terms of decibels. So where Pi is nothing but it's a mean input power that is launched in the fiber. And P naught is nothing but mean optical power that is secured at the receiver side. And CL is nothing but total channel loss. MA is nothing but, and it's in dispersion parameter actually. And DL is nothing but, and this is nothing but system margin actually. And DL is nothing but dispersion equalization, or we can call it as a ISA penalty, that is intersymbol penalty. And from this we can able to find out that is a mean input power that is launched into the fiber. And one more important parameter at the detector side is nothing but sensitivity of the detector, which is the minimum detectable power. So rise time budget includes the following factors. One is rise time of the source, rise time of the fiber, rise time of the amplifier, and rise time of the detector. So by finding all these parameters, we can able to find out. So the rise time budget is assembled as by using all these parameters together. System rise time budget, that is system rise time, is equal to 1.1 of Ts square plus Tf square plus Td square plus Ta square whole root. So where Ts is nothing but rise time of the source, and Tf is nothing but rise time of the fiber, and Td is nothing but rise time of the detector, and Ta is nothing but rise time of the amplifier. And these are all the formulas that can be used for the system rise time. And suppose if it is in non-return to zero data, then we can use that formula as T system is equal to 0.7 by, that is the bandwidth, BT. And for return to zero, we can use it 0.35 by BT. So this is the formula we can use it for rise time budget. Answer this example. Say for example, we need to design a digital link and to connect two points 10 km apart. The bit rate needed is 30 megabits per second with bit error rate of 10 power minus 12. Determine whether the components listed are suitable for the link or not. So this is the question. So these are all the parameters given. Source. So we'll be using LED with wavelength of 820 nanometer, and which is made up of gallium arsenide aluminum, which couples the 12 microwatt into 50 micrometer fiber and rise time of 11 nanoseconds. Next to that, medium, that is fiber. So the type of the fiber used is strip index fiber with the core dia of 50 micrometer, numerical aperture of 0.24, and 5 decibel per kilometer loss. Dispersion is 1 nanosecond per kilometer. There are 4 connectors with 1 decibel loss per connector. And the third part is detector. So the type of the photodetector used is pin photodiode, and responsivity is 0.38 A by watt, that is amps per watt, and junction capacitance is 1.5 picofarad. Dark current is 10 picoamps. Rise time is equal to 3.5 nanoseconds. minimum mean optical power is minus 86 dBm. And the question is, calculate also the signal to noise ratio of the link if load resistance RL is 5.3 kilo ohm. So this is the question. So we'll proceed with this solution. For this example, there are three factors that has to be considered. One is bandwidth, second one is power levels, third one is error rate, that is signal to noise ratio. So rise time budget. So according to the rise time budget, we know that. So there are two coding system. So we start with the rise time budget. Assume that. So there is a non-return to zero coding. The system rise time is given by zero point 0.7 by VT. So what is your here it is bit error rate is 30. 0.7 by 30 into 10 power 6. So therefore it is 23.3 nanoseconds. And therefore, and there is one more formula. So by using this formula, we can substitute all. Now we can assemble all the total system rise time as total system rise time is 23.3 nanosecond, what we calculated from the previous slide. And from the given statement, the rise time of the source is 11 nanosecond. Rise time of the fiber is 10 nanoseconds. And allowance for the detector rise time TD, and there is a formula to find out the TD. So it is 15.09. Now power budget. So total power launched into the fiber is minus 19 dBm. So losses, that is fiber attenuation 5 decibel per kilometer, so it is 10 kilometer distance, so it is 50 decibel. So there are four connectors connected. So each connector which will have the loss of 1 decibel. So therefore 1 decibel into 4, it is 4 decibel. Now the power available at the detector, we can write it as minus 19 dBm minus 50 dB minus 4 dB. So therefore it is minus 73 dBm. Since power available at this detector is minus the 73 dBm, the sensitivity of the detector must be less than this. So therefore the safety margin MA is equal to minus 73 minus of minus 86 dB. So therefore it is 13 dB. So from this, what's the conclusion is from the rise time budget and link power budget? The conclusion is that the choice of components are suitable because TD, which is calculated as 15.09 nanosecond, which is greater than that of the given TD value. So the total power available at the detector is, which is also greater than that of minimum power required by the detector. So here it is given it is 86 dBm. So what we got that value of MA is positive, that is 13 dB. So therefore the choice of the components are suitable. So that is a conclusion for the example. We can just move on to the example 2. So this is the second question. An optical link is to be designed to operate over an 8 km length without repeater. The rise time of chosen components are, so it has the that is a rise time value of 8 nanosecond, fiber intermodal 5 nanosecond per kilometer, intramodal 1 nanosecond per kilometer, detector 6 nanosecond. From the system rise time considerations, estimate the maximum bit rate that may be achieved on the link using non-return to zero code. So this is the question given. So we know that the formula is 1.1 of, actually it is root of, so ts square plus tf square plus td square. So by taking that whole root, we can just have that total system rise time as 46.2 nanosecond. So now from this we can able to find out what is the maximum bit rate. So bt maximum, that is actually t system is equal to 0.7 by bt for the non-return to zero code, we know that. So from that we can able to write what is the maximum bit rate required. So bt is equal to 0.7 by t system. So therefore by substituting this value, we will have 15.2 megabits per second. So this is the conclusion from this. So maximum bit rate of 15.2 megabits per second, or you can see that 3 decibel optical bandwidth of 7.6 megahertz. So likewise we can able to find out the what is the maximum bit rate by using this. Next one is example 3. The following parameters were chosen for a long haul single mode optical fiber system operating at 1.3 micrometer. So these are all the given statement. Mean power launched from the laser is minus 3 dBm. Cabled fiber loss is 0.4 decibel per kilometer. Splice loss is 0.1 decibel per kilometer. Connector loss at transmitter and receiver is 1 decibel each. Mean power required at the APD Suppose if it is operating at 35 megabits per second, then it is minus 55 dBm. When operating at 400 megabits per second, then it is minus 44 dBm. Required safety margin is plus 7 dB. Estimate maximum possible link length without repeater when operating at 35 megabits per second. It may be assumed that there is no dispersion equalization penalty at this stage. This is question number. Question number 2. Maximum possible link length without repeaters when operating at 400 megabits per second. Third question is the reduction in the maximum possible link length without repeater of B when there is a dispersion equalization penalty of 1.5 dB. So there are three questions from this solution. The first question, so they have just given that the maximum possible, there is a the maximum possible link length, and that is when operating at 4, that is 35 megabits per second. So the formula is Pi minus P naught. So that is equal to fiber cable loss plus splice losses into L plus connector loss plus MA safety margin of in terms of decibel. So fiber cable loss, which is given as minus 3 dBm, and here it is splice loss is given as minus of minus 55 dBm, and which is equal, that is Pi minus P naught is minus 3 dBm minus of minus 55 dBm, which is equal to fiber cable loss of 0.4, splice loss of 0.1 into L, connector loss of 2, and MA is equal to 7. So therefore, here by we can write it as the right hand side, it is 0.4 plus 0.5, and it is 0.5 L, and we can just add all dBm together. So here it is 52, that is 55 minus 3, it is 52. If you just take this 2 and 7 here, minus 2 minus 7, so from this we can able to find out what is the length L. So it is 86 kilometer. And the second question is, again it is, we have to find out what is the maximum possible link length with repeaters, that is without repeaters, when operating at 400 megabits per second. So again the same formula, so we have to substitute that values according to the 400 megabits per second. So we'll be just finding out this value. So here by separating this two, we will have the value of 41. So minus 2 minus 7. So from this we can able to find out what is the L. It is 64 kilometer. And for the third case, here we'll be considering that there is a dispersion equalization penalty of 0.5 dB. So that has to be considered. That is including dispersion equalization penalty of 1.5 dB. So here we can just add it DL here. So it is 1.5 is added here. The remaining formula is same. So from this we can able to find out what is the maximum length that is allowed between transmitter and receiver. That is 61 kilometer. So here what's the conclusion from this A, B, C is nothing but, and there is a reduction of 3 kilometer in the maximum length without repeaters when there is a dispersion losses taken into account. So that is a conclusion example. Thank you for your patient listening.